Discontinue.
So, very good morning and good afternoon to all our esteemed members of International Society of Photogrammetry and Remote Sensing and Indian Society of Remote Sensing, and all the students, faculty members, and professionals working in the field of remote sensing, and the student communities also, professionals, and all the members who have joined today for this webinar. So this is the webinar where we are lucky and also privileged to have Dr. Mark Drinkwater as one of the speakers for today's talk. Before we start, I will just give the brief introduction about Mark Drinkwater. He is currently head of Earth and Mission Science Division of European Space Agency. And ESA's Earth and Mission Science Division, it provides the scientific expertise for preparation, development, and operation of ESA's Earth observation satellite missions, including research missions, for example, Earth Explorer missions, operational meteorological missions, where you have some of you might have used the METOP series of the weather satellites, Earth Watch, and the Copernicus Sentinel missions, which are in last few years has gained very much big popularity among the user community. And Dr. Mark has more than 35 years of combined experience in the research for NASA at JPL Caltech, and also with the European Space Agency at ESTEC Norway, the Netherlands. He is specialized in Earth system science using satellite remote sensing techniques, and he has been responsible for scientific research projects in connection with NASA, JAXA, and ESA satellite missions, including the one of the earliest radar mission known as the CSAT. Some of you can explore this data freely from 1978 onwards. Then we have very successful missions like CIRSE missions and NSCAT mission of ADO's T-Winds, QuickSat, ERS2, NVSat, METOP, and many more. And recently, he has been the mission scientist for the successful missions like Cryosat, GOES, ASMOS of ESA's Earth Explorer, and Copernicus Sentinel-3 mission. Today, his team continues to provide support to ASMOS, Cryosat, SWARM, and Earth Care mission operations while supporting the ongoing development of biomass, which is a well awaited mission of ESA, FLEX, Forum, and Harmony. Harmony, again, it is a digital elevation model which will be very useful for the cryosphere community, together with the Altis, Truth, Sentinel-4, Sentinel-5, and 6 Copernicus expansion sentinels like SHIME, CMR, CO2M, crystals being very important for the cryosphere point of view community, LSTM, and ROSE-L, which is the L-band synthetic aperture radar, and METOP second generation series, and Arctic weather satellite. And his division are currently involved in preparing 6 new future Earth Explorer 11 and 12 mission candidates, together with cycle of all scout small mission ideas. And he has expertise in cryosphere and climate, polar, ocean, and gravity research, airborne and in situ campaigns using satellite remote sensing data. And he has coordinated data collection efforts with 13 international space agencies during the 4th International Polar Year, and also founded and chaired the World Meteorological Organization's Polar Space Task Group. So we are really honored, Dr. Mark, to hear from you. And on personal front, I remember Dr. Senthil Kumar, our earlier director at IRS, you used to give your example that we shared some of the RISAT images with your group, and then your group was also interested, was impressed with the CIs and all features what you could identify. And then there was some collaborative academic research work in that field. So we are truly honored to listen to you, sir. And I could see the very good and exciting missions, not just present, but in the future also, what your group and the ESA and Copernicus will be giving to the scientific and the academic community. So welcome, sir. Floor is yours.
Thank you very much, Dr. Thakur. And it's my honor to present today ESA's contributions to a global cryosphere observing system. I have experience from 2 space agencies in the world, from NASA and ESA, and so I'd like to bring a perspective about how to put together a cryosphere observing system capability, particularly from the perspective of deriving climate relevant data sets and climate relevant essential climate variable records. So let's just discuss the cryosphere first of all. This is a fuller projection of the world. It shows the key elements of the cryosphere, including both the polar and the subpolar regions. You can see the cryosphere includes all portions of the Earth's surface where we have water in its solid form. And so in the presentation, we'll be concerned by the sea ice, marine ice on the surface of the ocean, ice on lakes or rivers, snow, glaciers, ice caps, and ice sheets. I won't deal specifically with frozen ground because remote sensing techniques today can only detect permafrost or subsurface frozen ground indirectly. And so I'll focus largely on the types of climate records that we have from direct measurements of the cryosphere. So the cryosphere includes, in this case, high latitude Arctic and Antarctic polar and high mountain regions. And obviously the cryosphere is part of the Earth system which is experiencing accelerated changes due to rising atmospheric and ocean temperatures, together with the accompanying feedbacks in the climate system. Now, what we need is a comprehensive observing system to be able to understand which processes are driving the changes in the cryosphere. We also need that capability to understand the societal impacts of the changes in the cryosphere. And we also need to develop capability for forecasting, for developing products and services which help us societally to cope with the rates of change in the cryosphere. And so we need adequate data from satellites which are designed and purposely built for this purpose. And those are crucial to enable us to improve the forecasts of what the climate is doing in terms of changes in the cryosphere. This allows us to better predict climate, water resource availability, sea level rise, and also to have an appreciation of the impact of the cryosphere on shipping, for navigation, safe navigation purposes, for fishing, etc., as well as many other practical applications. And so satellites have become the mainstay, if you like, of the cryosphere observing system. Many of the parts of the globe with the cryosphere are remote and difficult to access. And of course, satellites provide a perspective which is unattainable by the combination of in situ measurements that we're able to derive today. So they provide today a constant source of information to sustain environmental services, and with particular focus on the cryosphere. Now, the high mountain and polar regions remain mostly undersampled. And so what I'd like you to appreciate by the end of the talk is the degree to which we need a coherent international and federated effort if what we want to accomplish is a very comprehensive federated cryosphere observing infrastructure. And I'd like to discuss some of the drivers of how we develop our missions in Europe for this purpose. And I'd like you to appreciate by the end the amount of effort that goes into putting together data sets to enable us to have a comprehensive overview and perspective of what's going on in the cryosphere today. Now, if we turn attention to Europe, we have some policy drivers for how we derive our funding for the development, in particular of the Copernicus Sentinel missions. The European Commission and the European Union's foreign affairs and security policy led to the development of an integrated policy for the Arctic. And this is one of the mainstays for justifying, if you like, the development of Sentinels, which enable us to collect data in the polar regions and in the cryosphere in general. Now, the policy calls for mitigation and adaptation actions, and this allows us to drive the development of system capability for measuring climate change and safeguarding the Arctic environment. It also allows us access to information for sustainable development in and around the Arctic, particularly for sustainable exploitation of natural resources, the fisheries in the Arctic, blue economy applications, safe navigation. And finally, it also enables us to federate countries and to better cooperate by enabling access to information across the entire pan-Arctic domain. And so Europe has policy directives which allow us to justify the funding for development of some of the Sentinel missions. And that's a very important piece of background, because without that, we'd have to assemble the funding and the finances across multiple member states for development of our satellites. Now, what are the important cryosphere parameters? Now, if we go back to the cryosphere theme report, which developed by multiple partners in 2007, this was developed to prepare the International Polar Year. Some of the main cryosphere parameters which the IGOS theme report identified of being of highest priority are gravity and geoid, sea ice extent, concentration, thickness and dynamics, or the movement of the sea ice, ice sheet, glacier mass balance, floating ice shelf extent and thickness change, snow cover extent, water equivalent of snow, the albedo and snow ice surface temperature, and also permafrost degradation. This is, of course, an indirect measurement, and that's the reason why I don't focus particularly on it later in the talk, although we do have permafrost products today being developed by ESA. Now, these products, the parameters are measured using a variety of satellite-based sensors and instruments, including principally microwave instruments, which comprise radar altimeters, synthetic aperture imaging radars, and radiometers. And then we also have optical sensors, which are, of course, limited by daylight in the polar regions and high latitudes, and also gravimeters. And I'll come to the types of products that we put together using these combined sensors in just a moment. But first of all, the importance of the oceans and the cryosphere have been highlighted in the International Panel on Climate Change's report on oceans and the cryosphere. This was part of the 6th assessment report. This has highlighted the importance of climate change in the cryosphere and the polar regions. And many of the results which were published in the last special report on the oceans and cryosphere as part of the last 6th assessment report published in 2019 comprised data which came from some of our essential climate variables describing changes and the rate of change in the cryosphere. Some of the examples shown here, for instance, are the rate of sea level rise as a consequence of ice sheet mass loss. We can see on the left the rate of sea level rise measured by the satellite altimeters in our Copernicus records. And you can see on the lower right the rate of ice mass loss. And so we're able to monitor how mass change is influencing sea level using the combination of data today in the Copernicus system. I'd like to dig a little bit more into detail then about how we put our essential climate variables, such as the sea level record or the mass change impact on sea level, how we put that together. And so in the following slides, I'll show some examples. But first of all, as background, the majority of our satellites are polar orbiting satellites. These allow us to cross the pole and the cryosphere typically 15 times a day in the high latitudes. This enables to build up measurements over time using the combination of the satellite instruments. And this allows us to use a combination of microwave or optical instruments for measuring either throughout the polar night or throughout the austral summer or the Arctic summer. And through this combination of optical and microwave capability, we're able to put together a variety of measurements 24/7 year-round to start to develop the climate records that we're interested in for climate change research. But let's just give an overview of our programs, first of all, so that you have an appreciation of the different types of and the array of missions which Dr. Thakur introduced in my bio at the beginning. We have a number of different programs illustrated by the 2 rings in light blue on the left, by the 2 central dark blue rings, and by the purple rings. These are our research programs in light blue. Within our research mission program, we have small missions or missions of opportunity, scouts and missions of opportunity on the left ring. We have our Earth Explorer research missions in the second ring. In the two central rings, we have the Copernicus Sentinels, which are part of the current observing infrastructure of Copernicus today. We have the Copernicus Expansion Sentinels, which I'll come to, which are new missions in development right now, which will be coming online in 2028. And on the right, we have the operational meteorological satellites, which we develop on behalf of EUMETSAT, the European Meteorological Satellite Agency, who operate our satellites once they've been developed. So we have a rather comprehensive array of Earth observing capabilities developed within these different programs. And this is the result of years of innovation, planning, and foresight, together with progressive transfer of many of the technical capabilities from the Earth Explorers into the Copernicus Sentinel domain. It's also the legacy of our missions in the early 1990s and 2000s, which comprised missions like ERS or MVSAT. And we've been able to continuously infuse the Copernicus Sentinels with technologies which have been inherited, if you like, from the Earth Explorer and the research mission domain. Now, many of these satellites have and will contribute valuable data to cryosphere research because of the fact that the majority are in a polar orbit. Some of these have been designed very specifically for cryosphere observations, and I'll come to that as we illustrate how the essential climate variable records are put together. But this gives an overview of the Copernicus space component evolution. Copernicus is very important to constructing climate records because it gives us a continuous operational perspective. We have operational continuity in the missions, and the idea is to develop a continuous record from the combination of several different missions. Now, the first generation of Sentinels began in 2014-15 with Sentinel-1. And the idea is to have a 15-year continuous record of that first generation of 6 series of pairs of satellites. These will be replaced in the early 2030s by the next generation Sentinels, and they're currently in development right now. In addition, we have the green Sentinel expansion, which will start to come online in around 2027, 2028. And I have a slide illustrating later the series of 6 satellites which within the Sentinel expansion, which will help to complement for some of the cryosphere parameters that we're interested in. So this shows all of the Sentinels together. At the left, we have the current generation Sentinels. We have pairs of satellites currently in orbit for the blue highlighted missions. And there's an A and B satellite which are operating in parallel to acquire global coverage. We'll be launching very soon the C and the D units of the first generation, and they will be followed by next generation Sentinels, for which we now have new missions in development for the next generation of Sentinel-1, 2, and 3. And on the right, we have new Copernicus Sentinel expansion missions, which will be coming online later this decade. The most important ones for the cryosphere and the polar regions are the Copernicus Imaging Microwave Radiometer, or SIMR as it's known, Crystal, which is the polar ice and snow topography altimeter, and also Roselle, which is the radar observing system for Europe at L-band mission. This is L-band synthetic aperture radar for monitoring the cryosphere to complement the C-band of the Sentinel-1 first generation and next generation radar missions. So that's the overview of the Sentinels. And now let's wind up the background by reminding of not only the need for continuity in the space-based observation elements, which are provided by the Sentinels in the first and the second generation, but of course, continuity must also be balanced by building a perspective for both receiving and processing what are massive and sobering volumes of data that come from the Sentinels. And when we have an infrastructure of this size and nature, we have to also plan for not only the downlink, but also the delivery of a massive volume of data, which amounts to over 250 terabytes of data, which are disseminated daily by the series of Copernicus Sentinel missions. And so together with the observing system infrastructure, you need a coherent plan for the effective treatment of the data volume. We need a perspective for not only the development of the operational products, but also the way to distill those products into important variables and data records, which can be delivered on a routine basis. So let's get to our climate program. We've been developing so-called essential climate variable data sets from the combination of all of those data from our research and operational missions. Today, ESA's Climate Change Initiative, which is known as CCI, has developed 25 different essential climate variable data sets, each comprising multiple satellite products. These can be from multiple satellites across multiple agencies. And I'll come to how some of the cryosphere essential climate records have been constructed in just a moment. CICE is highlighted at the top here. For each of these records, which you can find at our website, freely and openly available at climate.esa.in, the cryosphere essential climate variables are sea ice, Antarctic ice sheet, glaciers, Greenland ice sheet, permafrost, and snow records. Within each one of those essential climate variables data sets, we can see a multiple of data sets comprising different styles of products which can be accessed at the hyperlink at the base of the page there. Now, if we think about integrating data sets into essential climate record, I'd like to use an example, first of all, for integrating the fundamental climate records derived by different satellites into a single essential climate record for, in this case, the Greenland ice sheet mass balance. This figure comes from our project called the Interagency Mass Balance Intercomparison Exercise, which we've been constructing this data set together with our NASA colleagues. This paper by Otosaka et al. In 2023 shows the impressive number of different data sets which are required to put an essential climate variable together, such as the mass balance of the Greenland ice sheet. This data record comprises 14 different satellites from ESA, NASA, CSA, ASI, JAXA, USGS, and DLR. And perhaps the most important message from this paper is the effort required behind the scenes to assemble a climate record from these multiple data streams to allow us to construct a contiguous climate record over the interval from 1992 until the present day. This, of course, required also not only interagency cooperation, but it also required some extensive data acquisition planning. You can see that during the period 2007 through 2009, during the International Polar Year, for instance, we had 8 out of the 14 different satellite data streams being acquired in parallel. And that was thanks to the extensive effort within the World Meteorological Organization's Polar Space Task Group. In that group, we were coordinating the acquisition planning between the different satellites to enable us to put together this kind of ice sheet record for mass balance. Now you see at the left that the essential climate variable also integrates SAR, or synthetic aperture radar imaging data sets, together with altimetry and gravimetry at the bottom. And I'll go into a little bit more detail now about how those data sets are put together in the following slides. So how do we combine the different satellite data sets into an ice sheet essential climate variable data set? Well, this shows a nice chart, which is from William Colgan. It illustrates the combination and the use of different data sets, in this case, satellite, airborne, and ground-based, to get a comprehensive understanding of ice sheet mass balance. On the left, we have the imaging radars from the different agency SAR missions, including our EMISAT and Sentinel-1 missions. These provide information on changes in the surface velocity of the ice sheet. We combine those with satellite altimetry in the central part of the slide here. There we have the ISAT, Cryosat, ERS, ENVISAT, and Sentinel-3 radar altimeter records of surface elevation change. And then on the right, we're able to get an integrated mass change perspective from satellite gravimetry, and we get that from the GRACE follow-on and the Gautier ESA gravimetry mission. And I'll show you some examples of these types of products in the following slides. So first of all, an ice sheet elevation change and dynamics. Here we're combining the records from Cryosat altimetry, Sentinel-3 altimetry, and Crystal in the future to derive an unbroken surface elevation and surface elevation change time series over Greenland and Antarctica. This shows the Greenland example from 1992 until the present day. The Crystal dual frequency altimeter will be enable us to extend this time series from 2028 onwards. And if I add the information now illustrating the type of data in that ice sheet elevation change, here I show 5 epochs, each of 5 years, showing the changes in the rate of change of ice sheet elevation over Greenland over time from this climate record. Now at the bottom, we also can combine that elevation change together with the velocity on the ice sheet, the calving front location changes, and also the ice discharge changes. Now there we're combining synthetic aperture radar, ice surface velocity measurements into the essential climate variable record. We map the calving front location changes over time, and we can turn using various methods the velocities into ice stream discharge, and there we can plot the time series discharge for all of the glacier basins in Greenland. Now this allows us within the climate change initiative to provide contiguous products of each of these parameters, and I'll show you some examples now. This shows the ice sheet velocity time series. From the planning of the variety of SAR data acquisitions, we're able to get a continuous record of the velocity around the periphery of the ice sheet over the majority of the year. And then in the winter months where we have the best coherence in the C-band SAR repeat imaging, we're able to get a contiguous view of the ice sheet in the winter months. And so this allows us to plot month by month changes in the velocity over the entire Greenland ice sheet. This has enabled us to prepare an essential climate record of the velocity, and this is also allowing us to translate the velocities into the ice discharge in each of the glacier basins around Greenland, allowing us to monitor how the variability in the ice sheet discharge is influencing sea level globally. This gives an illustration of how Sentinel-1A and B data are being combined, and this shows the imaging data over one of the outlet glaciers, in this case Jakobshavn ISPRS in Western Greenland. This shows how the launch of the second of the pair of Sentinel-1A and B satellites enabled a much better perspective in terms of the variability in the ice discharge on a per glacier basis around Greenland. The combination of 2 satellites counter-rotating in orbit allows us to obtain a far shorter revisit. We halve the revisit with 2 satellites from 12 to 6 days. And this gives us a much better temporal resolution of the variability in the ice discharge from the glaciers. Perhaps the most important feature of this improved temporal resolution is the fact that at 6 days, we also have better coherence between the repeat images. This allows us to measure velocities far closer to the calving front of the glacier in Jakobshavn ISPRS. And it allows us to resolve then the seasonal variability in the velocity at the ice front. which, as we can see, increases in the summer months when meltwater is percolating down to the base of the ice sheet, and it's lubricating the flow, enabling the flow in the summer months to speed up. So we can see that not only the combination of the A and B satellites is important here, but a sustained time series is important to be able to construct not only a seasonal, but interannual variability and the ice discharge from each of the glaciers around Greenland. Now we are trying to combine that information in a cumulative ice mass loss perspective now. These data have been integrated into the Copernicus Climate Change Service, and we're now moving on to synthesizing all of the information into a cumulative ice mass loss perspective. This is an interesting paper from Green et al. This was published in Nature this year. It shows how we can now integrate all of the cumulative mass loss from each of the respective individual glaciers, which is represented by one of these colorful time series. If you add cumulatively each individual glacier together, we have 243 outlet glaciers around Greenland from which the discharge can be measured using this combination of data. This allows us to add up the combinations of the different glacier drainage basins. And we can see that the cumulative addition of all 243 glaciers, including the most sizable ones, Sakarya, Humboldt, and Jakobshafen, add up to over 1,000 gigatons of ice over the time period from the mid-80s until 2022, using all of the data sets which are available for constructing the climate record. Now, nearly every glacier in Greenland has thinned or retreated over the past few decades, leading to glacier acceleration and increased rates of sea level rise and associated climate impacts around the globe. This result shows how the mass loss varies in the different glacier basins, and you can see the red glacier basins where we have the largest and most significant mass losses recorded between 1985 and 2022. We can see that Jakobshaven is in Western Greenland is still one of the main contributors, although Sakarya Istrum, the northeast ice stream, as it's called, which discharges into the Greenland Sea and northeastern Greenland, is now cumulative discharge is one of the largest out of all of the glaciers in Greenland. Now, on seasonal timescales, Greenland loses around 193 gigatons of ice to retreat each year from a maximum extent of the ice front in each of the terminating glaciers in May to a minimum between September and October. So we can see that many of the floating glaciers which discharge into the ocean have a seasonal advance and retreat as they calve. We find that multi-decadal retreat is highly correlated with the magnitude of the seasonal advance and retreat of the glaciers, meaning that we have quite a significant variability in the terminus of each of the glaciers over time. And that's the reason why we need to monitor the calving front location of each of the glaciers to understand the glacier sensitivity to the longer term climate change. Now, if we switch attention to what's going on in Antarctica, Antarctica has not been contributing as much to sea level change, sea level rise as Greenland has, where Greenland is suffering from far greater degree of melting in summer months. Nevertheless, with Cryosat, we've been monitoring quite dramatic changes through the deflation of the ice sheet surface in areas where changes in flow have a dynamical consequence for the shape of the ice sheet surface. We also note that the ice shelves have been thinning around West Antarctica as the ice is discharging into the ocean, with the result that the grounding line is retreating. Now, one of the factors which is now understood to be responsible for this recession in the grounding line and the thinning and retreat of that grounding line location are the locations around Antarctica where circumpolar deep water and warm water comes up in contact with the base of the ice shelves and at the grounding line location. And this is thought to be responsible now for the acceleration in grounding line retreat, particularly in West Antarctica, which is most susceptible to the warm deep water coming into contact with the glacial cavity beneath the ice shelf. So West Antarctica is thought to be the most sensitive part of Antarctica to change. And this recession in the grounding line and the associated dynamic thinning of the ice streams results in something called marine ice sheet instability. Because we have a retrograde or sloping bedrock underneath West Antarctica, this grounding line retreat allows more and more warm water to penetrate into the glacial cavity. And this process is thought to be responsible for destabilization in future of the West Antarctic ice sheet. And so this is one of the processes which we have to keep a close monitor of to understand how these feedback mechanisms influence the loss of ice from the West Antarctic ice sheet. Now, if we turn briefly our attention to the other dimension of ice sheet surface change with optical instruments rather than the microwave instruments we've just shown. In the frame of a project called ESA, researchers from Denmark, France and Germany have been developing methods for using the optical products from the OLCI, the Ocean Land Color Instrument, on board our Sentinel-3 satellites. And they're able to reconstruct information about snow grain size and the albedo, the surface albedo, broadband albedo of the ice sheet. And they are able to successfully map now the surface melting of the ice sheet and the resulting albedo change in the summer months. And so here we see an example of the albedo anomaly from one year to the next. And here you see a movie showing a reconstruction of the interannual variability in seasonal and interannual variability in albedo as mapped using the Sentinel-3 products. So not only do we have information now about changes in mass balance and elevation, but we also have information about the albedo anomaly and the resulting energy imbalance or energy balance changes at the surface, which are contributing to either surface melting or deflation in the surface as the consequence of atmospheric changes or atmospheric warming or snow changes in snow accumulation. So let's change to understanding how we constructing gravity records, because gravity is also fundamental to understanding how the meteorological instruments like altimeters and SARS can be used. Importantly, gravity satellites like our GOCHE mission, the Gravity and Ocean Circulation experiment between 2009 and 2013, that allowed us to access data using the gradiometer and 3 pairs of accelerometers on board the satellite, which enable us to measure gravity gradients in the XYZ direction with respect to the Earth reference frame. This allowed us to measure a high-resolution static Arctic gravity field and a geoid, which is important because it's used for computing the orthometric heights above sea level. And it's also used as a steady-state reference for the ice elevation change and ocean dynamic topography changes, as well as changes in sea level. And so GOCHE is also a fundamentally important data record for measuring mass change and sea level change in the Arctic. And we're progressing towards development of a new mission together with NASA called MAGIC. MAGIC is the ESA-NASA Mass Change Geosciences International Constellation, as it's known. This is going to comprise 2 inline pairs of a mission like GRACE today, except we'll be comprising the 2 pairs of missions in what's known as a Bender constellation. So one pair, which is NASA's GRACE-C mission in blue, indicates one set of orbits in high polar inclination. And we'll have a second pair of satellites combined at lower inclination orbit to provide a much more dense spatiotemporal coverage, which will allow us to access near real-time data at sub-weekly timescales, and it'll also enable us precise monthly and trend solutions from the combination of the two mission data sets. And so this mission's planned in the early 2030s, and we're currently in the process of nailing down the finances to go ahead with the development. GRACE-C is already approved on the NASA side, and so it just relies on us completing the second pair to enable this mission to take place in the future. But that allows us to not only continue mapping the geoid in the Arctic, it'll also allow us to continue making direct measurements of ice mass changes, like the ones which are being made from GRACE and GRACE follow-on today as part of the Essential Climate Record. So let's switch attention to sea ice, to the sea ice essential climate variable. Here we're measuring extent, concentration, sea ice type, and dynamics. And there we're using a combination of scatterometer data from METOP, ASCAT instrument. And in the future, we'll be using the METOP second generation instrument, as well as the CIMA, Copernicus Imaging Microwave Radiometer. These provide today daily low resolution ice extent, concentration, type, and drift from the combination of SSMI and METOP. And in the future, we'll use the second generation METOP satellite instruments together with the Sentinel expansion CIMA mission from 2029 onwards to provide continuity in these data. For sea ice, we also have the capability offered by the higher resolution C-band SAR on Sentinel-1, followed by its next generation, and also complemented by the ROSE-L Sentinel expansion mission, which I explained earlier. These provide today high-resolution sea ice, drift velocity and divergence, shear and ice type charting. We're also able to map icebergs around the coast of Greenland in the Arctic. And the combination of ROSE-L and Sentinel-1 will enable continuity in this operational ice mapping in the future. This shows the synergy between ROSE-L, the L-band SAR instrument at 1.2 gigahertz, and the Sentinel-1 next generation in the future, which will provide continuity of the 6 gigahertz C-band data set. You can see the combination of these data allows us to derive synergetic sources of information about sea ice and sea ice changes in the Arctic. The complementarity between the resolution and the orbit will allow us to not only provide continuity to what's in the Sentinel-1 data today, but the L-band information products will allow us much more accurate ice charting information in the future. So let's switch attention to sea ice freeboard and thickness. This is also part of the sea ice essential climate variable record. Today, we're combining Cryosat and SMOS in this important time series of thickness changes in the Arctic and Antarctic. This shows an example of the Arctic sea ice thickness changes in the top right movie. You can see an example of how we exploit the complementarity of the passive microwave L-band radiometer here, which is able to derive sea ice thicknesses up to about 0.5 meter. It's most sensitive to thin sea ice thickness. And we combine that information with the Cryosat data record. Cryosat's most sensitive to the thick part of the sea ice thickness distribution. And using the combination of those products, the Alfred Wegener Institute is today putting out these data records showing contiguous sea ice across the Pan-Arctic basin. Now, for the thickness time series shown in the lower plot, we're using the altimetric record. This allows us to construct sea ice volume changes in the Arctic of the multi-year ice in green, and the seasonal first-year ice in purple, and then the total volume of the ice in the Arctic on an interannual time frame. This is now using the combination of Cryosat and Sentinel-3 altimetry, which are providing coverage up to 88 degrees north over the Arctic. We're currently in the process of improving the sea ice thickness retrievals so that we can extend to the Antarctic. This is the latest paper by Fons et al., which is showing how using improved thickness retrieval capability with Cryosat, we're able to derive now also thickness variability and volume interannual variability in Antarctica using the Cryosat record. And so we now have a bipolar record of sea ice thickness and volume using the combination of the altimeters. And we'll be looking to extend this with the crystal data in the future. Now, just a little bit about crystal to enable you to understand what's involved in the crystal mission, which will be coming online in 2028. This is based on Cryosat 2 heritage, but with significant improvements. And we have added a Ka band channel to the Ku band channel of the SAR altimeter. And we've also added a passive microwave radiometer. This combination of instruments in this suite allows us to derive snow information on the surface of the sea ice. And snow up until now has been the most confounding issue with respect to deriving accurate sea ice thickness retrievals. And so in terms of performance improvement, we expect to improve the sea ice freeboard measurement by 36%. By increasing the bandwidth of the SAR altimeter instrument and coupling it with the second frequency and the passive microwave. And so we're looking forward to the crystal mission to enhance and improve the capability within Copernicus for sea ice thickness and ice sheet mapping in future. This gives an illustration of the different modes of the crystal over the sea ice in the case shown here. We also have iceberg detection and ice sheet detection modes. Here you see Cryosat flying over the ice sheet, and you can see the standard products on the left in the table, together with the latency of the data products, which we'll be producing in both near real-time (NRT) standard time processing, and then we'll also have climate offline processing for precise records, particularly for the ice sheet elevation change and its contribution to sea level. So that's crystal and how it can be added in the future. And finally, snow cover before I wrap up the presentation. Snow cover area and water equivalent, as well as lake ice extent, are some of the other important essential climate variable records that we're producing. But these are obviously produced by optical missions and optical instruments. ESA's Snow CCI project generates the global snow cover area and snow water equivalent products. These are generated using optical images from METOP AVHRR and Sentinel-3 SLSTR. And these have all been integrated into the Copernicus Global Land Monitoring Service today. You can see examples of the products at the right. For the snow ECV, we have the global snow area extent at the top right, computed using a combination of medium resolution products from AVHRR, MODIS, ATSR, and SLSTR. The upper panel shows the snow cover fraction product for the 6th of March in 2003. And we also have in the lower right passive microwave snow water equivalent products developed by the Finnish Meteorological Institute in the Globe Snow project. These are all-weather global snow water equivalent products using a combination of SSMI and AMSA data. And these will be extended in future using the Copernicus imaging microwave radiometer satellite, together with the microwave instrument on board METOP 2nd generation. Now, all of these products, including lake ice extent, for instance, are all included and integrated today in the Copernicus Global Land Monitoring Service through the Cryoland Framework Project. And they're available for viewing through the Cryoland portal at the link, at the hyperlink shown here at the bottom. You're also able to download them from the Copernicus Land Service website. So I'd like to go back to where I began, which is about the integration of different satellite data products and the foresight that's needed to integrate many different satellite products into essential climate variables. Within Copernicus, we've been making special effort to try to understand how to combine the different missions. And this shows a series of examples to illustrate, first of all, in the top left, how we've synchronized the orbits of METOP second generation together with the Copernicus imaging microwave radiometer to make sure that we can combine SIMA and MWI data, as well as the other instrument data streams like AVHRR, so that we can combine them and obtain collocated data sets in time and space. In the central panel here, you see how we're combining SIMA, Sentinel-1 data. You can see we're able to combine active and passive data using the combination of the passive microwave radiometer and SAR by synchronizing the orbits over the polar regions and the cryosphere. At the top right, you can see how using SIMA together with Sentinel-1, we can get contiguous coverage. Lower left, we've got SIMA and ROSE-L. Lower central panel, we've got Crystal and SIMA. And lower right, we've got Crystal, SIMA, Sentinel-1. And so constructing a comprehensive integrated observing system relies not only on ad hoc efforts from space agencies, but it also relies on plannings with respect to the orbits, the time of day coverage, and how the orbits intersect over the cryosphere. And this relies on quite some foresight and planning of the different missions and constructions of the orbits even. And so in summary, I'd like to provide a synopsis of what I've talked about, and that'll allow us to wrap up and leave some time for questions. So ESA's been developing a whole series of new Earth observation missions to equip Europe with an expanded capability for monitoring both poles and the global cryosphere, and to derive sustained climate data records. We're taking into account new user needs. We'd like to take those up in the continuity of the climate records as well. But we observe that this relies on quite some foresight and planning, particularly because the development life cycle of new satellites and technologies is of the order of a decade or more. So we need to plan very far ahead if we want to foresee not only integration of new capabilities, but also to ensure continuity in the climate records. Now, in the past, the International Polar Year and the WMO Polar Space Task Group have taught us that coordination is required, not only in the acquisition planning, since most of the synthetic aperture radar instruments are on a planning, an image planning basis only. And so to obtain a coherent and consistent set of views of the poles and the cryosphere relies on quite some coordination of the acquisition and planning of those imaging instrumentation, and without which we wouldn't have a consistent set of observations for climate research. And that goes back to the example I showed for the Greenland ice sheet for the multiplicity of different SAR data records which go into the essential climate variable. So in conclusion, by contrast to 20 years ago, I think, I believe it's fair to say today we have an extremely rich and growing data archive for reanalyses and climate modeling and research. These data provide unparalleled scientific evidence for climate change. And these data are also critical for effective decision making and policy implementation in the future. They're, of course, also really important for development of the next generation of forecasting prediction systems, and particularly climate predictions, which rely on information about sea level rise and the relationship to ice sheet mass wasting. Further development of a coordinated space component of this global cryosphere observing system, of course, doesn't only rely on what we're doing within ESA, and we're committed to international cooperation and cooperation on an international basis. in order to do a better job of monitoring the global cryosphere, it's clear we need interagency efforts and multilateral cooperation on both the scientific and technical level. And efforts like the World Meteorological Organization's Global Cryosphere Watch are essential in the future, not only because they help to do the coordination across a greater number of nations, but they also help to integrate the satellite data with the in-situ data, which is collected through the monitoring network infrastructure that WMO is responsible for. So I hope that provided you with an overview of how comprehensive an observing system we're trying to put together within ESA and how that can contribute to global cryosphere observations. And so I'd like to leave some time for questions now for you about the presentation. So thanks very much for the opportunity.
Yes, man. Yes, thanks, Dr. Mark, for the excellent lecture. And are you able to hear?
Yes, I am. Yes.
Yes. So not just ESA, but the global remote sensing and EO community has been well supported, and a lot of research I could see, especially in Sentinel series. Earlier, we had to pay for the radar data. Now, once the Sentinel series came, and it is a long time series, so a lot of interferometric, whether it is cryosphere, land subsidence, or the interferometric or the monitoring. So that has been supported and popularized by the Sentinel-1 missions, and also this Snap tool, where it provides open source free software to process. Otherwise, for processing also we had to buy some commercial softwares. So we have some questions. You can see the question answer
Yes.
center.
Yeah, the first question I can see from Sajpal Singh is how do we exactly measure, or how can we make a good measurement or approximation of snow and ice grain size from remote sensing data only? Well, there we have multispectral instruments on board our Sentinel-3 satellites. The multispectral instrument, OLCI, has a number of bands which can be used to obtain a spectral representation of the response of the surface of the ice sheet. And using the combination of different wavelengths, we're able to retrieve the snow and ice grain size at the surface of the ice sheet. And as I illustrated in the SICE project, this can be used to derive also the spectral response of the surface of the ice sheet. It can be used to derive the broadband albedo of the ice sheet surface. And then constructing this time series allows us to monitor not only the impact of the snow and ice grain size on the albedo, but it also allows us to understand how different portions of the spectrum are influenced by the ice sheet surface and the process of melting. So if we think about energy balance modeling, we can then use the snow grain information in models to understand how the spectral response of the surface influences reflection in different parts of the spectrum, and how that influences the overall energy balance. And that's quite an important ingredient in understanding how climate change not only influences melting of the ice sheet surface, but how the melting also, if you like, modulates or modifies the energy balance relationships, particularly in the summer months. So I hope that helps to answer the question about how we use Sentinel-3 data. There are a number of publications on this topic. And I can try to provide information, if you like, on sources of the literature where we show how the Sentinel-3 data are used in retrievals of snow and ice grain sizes. So the second question was about temporal coverage for snow water equivalent data. Today, we rely on global data sets from passive microwave for snow water equivalent. We'd like to, and they come from SSMI and AMSA traditionally, the AMSA records, which have been contributed by the US JAXA and the US Navy in the past. Now, these have been used to derive relatively coarse snow water equivalent data, coarse in space, 25 kilometers, and on a daily basis. In the future, we'd like to improve the temporal and the spatial resolution by adding SAR data, but the problem is in mostly in mountainous terrain. Passive microwave is useful over the plains and the flat areas of the world, where passive microwave can be used to do the retrieval. But we have a problem in regions of terrain, complex topography, where I believe in the future we need interferometric retrieval of snow depth and snow water equivalent. And there we need the longer wavelength ROSE-L L-band SAR data, I believe, as well as NISAR in future. And the combination of NISAR and ROSE-L can be used in an interferometric way to retrieve snow depth and therefore add to the information about snow water equivalent retrieval in mountainous terrain. So I hope that answers the question about snow water equivalent. Glacier velocities in dense debris-covered glaciers. Yeah, the debris-covered glaciers are, of course, a problem because of the coherence or decorrelation, particularly in L-band data. And that's one of the main reasons why we're not able to use C-band very effectively in debris-covered glaciers. We're hoping, of course, that ROSE-L will provide us with better coherence in those circumstances. And it's a situation where I believe we need to combine all resources and use optical flow as well as SAR-related or interferometrically derived velocities to derive the best combination of information for velocities in those types of circumstances. Snow and ice density from the data, very good one. You need, of course, snow density to retrieve snow water equivalent if you have snow depth. So you do need the combination of snow depth and density if you want to retrieve snow water equivalent. And so we derive snow depth by measuring the surface when there's no snow. And then if we were able to retrieve the snow depth interferometrically using SAR during the winter months when you have snow-covered ground, by subtraction, you know the depth. And then by using the combination of the different frequency SARs, we hope to recover information about the snow density, the snowpack density. Now, similarly, the passive microwave radiometer will give us access to this information because we'll have multiple frequencies. And in these multi-frequency retrievals, we have much better opportunity to be able to recover information about the snow properties. So we'll have passive microwave plus SAR in the future from a multi-frequency perspective, and I think we're going to be in a much better situation for developing information not only on snow depth but density and snow water equivalent using the combination of information available. Snap software. Yeah, that's a good one. As we add these Copernicus expansion sentinels, one of our goals is to continue development of the Snap capability so that we can integrate modules that enable us to use the new Sentinel expansion missions as they come online. This will enable the community through these open source tools to access the new products and hopefully to develop elements of the code in open source to enable us to continue to revolutionize the code and to provide new additional capabilities to both combine the different Sentinel data sets, but also to understand how in combination we can recover some of these difficult to retrieve parameters today, like the snow water equivalent in mountainous terrain. Is there imaging processing software other than SNAP to use for Sentinel data? Well, from my perspective, no, because that's the one that I'm most familiar with. Of course, there are other open source software available in Python that are available through GitHub that I know other scientists are making available openly in open source. And so if you scour the GitHub web, I know some of these are available through, say, the Alaska SAR facility, for instance, or through links at JPL. And there you'll be able to find other tools that are complementary to what we offer through SNAP, I hope.
Yeah. Thanks, Dr. Mark. So I have one question. This relates to the lot of competition among the Earth observation satellites. Earlier, we used to get excited with the core H2O for the snow water equivalent. So
Yes.
Is there any chance that such kind of missions will be revived, or
it's interesting you raised the question about Core H2O. Core H2O was an Earth Explorer candidate mission, which unfortunately didn't get approved for implementation. The idea hasn't gone away, and you can see how we've evolved the Crystal mission to include multiple frequencies. Core H2O wasn't an altimeter multiple frequency mission, but rather it was an imaging SAR multiple frequency mission. And the idea was to include two complementary frequencies, both to enable penetration through the snowpack, but to combine the different frequencies to retrieve snow water equivalent from a SAR. Canada have been studying this intensively the last few years, although I'm not sure that they've agreed to move forward with the development of the mission. In the meantime, what I can say is we're likely to receive another proposal very soon in the frame of our Scout missions, our Scout research missions. I understand the community is preparing a proposal for a constellation of small satellite-based twin frequency imaging SAR. And that might be the best possibility for further study on this kind of technology in the future. But I think the jury is still out on how best to retrieve snow depth and snow water equivalent in complex terrain. And that's something that we have to work on more, using combinations of the different SAR data when we have NISAR launched, when we have Roselle launched together with Sentinel-1 and Sentinel-1 Next Generation. And then we can really start to work on this problem of how to recover snow depth and density and water equivalent in mountain terrain, where we need complex digital terrain models. We need models which are able to cope with the slope and the aspect and the way in which the SAR viewing geometry influences the retrieval. And so there are many complexities in doing the retrieval that we have to really start to work on, I think, before we can have the perfect solution in space. But this is something that I know many scientists are working on now around the globe, and certainly the number of different complementary data sets that will become available in the next few years give rich opportunities for the science to really improve. Yeah.
So I think there is an interesting aspect of SWOT mission, surface water and ocean topography. Although for the ocean and inland water, the researchers have seen that Ka band also gives very good ice sheet elevation and the glaciers. So there is a possibility we can explore even the Crystal mission because it has a SAR mode with the Ka band. So the snow depth part, we can think of sorting it out.
For sure. And it's based upon the altimetric experience with predecessor missions like Altica, from which we derive the understanding of how to use a Ka-band SAR. This has been now employed in the instrument on the SWOT mission, and the surface water ocean topography mission is leading to the development of our Sentinel-3 next generation topography mission as well. And so Sentinel-3 next generation topo will also be an operational implementation of the SWOT mission in future. So we can look forward to having operational SWOT SAR altimetry in the future for the ocean, for lakes and hydrology, which is one of the topics of this seminar series, of course, as well as glacier surface mapping. And there, the goal will be to obtain SWOT mapping of all water and ice surfaces. And that should be our objective for the future, is to get a coherent time series over all global water and ice surfaces.
And I saw in your slides something about swarm mission also. So recently I read a paper from Professor Andrew Scarp. So that looks very interesting, that two passive receiving and sentinel transmitting. So that also giving you this information about the land ice.
Yes, and I did. So harmony. So you were talking about harmony mission.
Harmony, yes, yes,
Yes,
harmony mission.
yes, yeah. So harmony is a wonderful opportunity because what it's designed to do is fly two satellites in constellation together with Sentinel-1. We'll have Sentinels-1 C and D coming online, and Harmony is being developed to fly with them and the next generation of Sentinel-1, where we'll have a continuous transmitting satellite flying together with two passive satellites, which are flying around Sentinel-1 in a helical way, a helical orbit. This allows us different baselines for interferometry and imaging, for stereo applications, which will allow us ice sheet topography and glacier topography measurements very accurately. It'll allow for different baselines so that we can optimize the interferometry for different types of topography. And so Harmony is a passive C-band dual satellite constellation. It's currently in development for several years with a goal to fly in around 2030, 2031. And it's going to revolutionize what we can do with Sentinel-1. It'll be complementary, of course, but it'll give us access to these wonderfully precise digital terrain models and change in topography over time, which we understand to be really important for monitoring the glacier and the cryosphere mass change over time.
Yes, thank you. And from ISRO side also, we are planning this resource at sampler, which is a traditional photogrammetry mission. So by the next few years, we will have a very beautiful missions covering the changes in the elevation and the topography.
Yeah,
so
thanks for that complimentary information. I think the resource satellite opportunities together with the Sentinels will provide some wonderful combination products, particularly in high mountain Asia, where the number of satellites is important. Obviously, I talked a lot about the polar regions. If we go to the equatorial regions, polar orbiting satellites give far more sparse coverage over high mountain Asia, Hindu Kush, Himalaya regions, where water resource management is fundamental, particularly in India, Nepal, Bangladesh, etc. There we need to improve our capability for the monitoring, because polar orbiters, single polar orbiters don't do enough in terms of the spatial coverage or the temporal revisit. And if what we want to do is to monitor the water resources in the snowpack, and how the snowpack is, what the persistence of the snowpack, and how does the snowpack vary from one year to the next. There we're going to need combinations of satellites from multiple agencies in order to do the job most effectively. So that's the reason why I stress the interagency cooperation. And we need organizations like the WMO and the Space Task Group, together with CIOS and CGMS, the coordinating groups amongst the space agencies, to make sure that these combinations of satellite products give us the best opportunity to do this science and to provide these societally relevant data sets in the future. I think that's fundamental, and so the cooperation is really the key there.
Yeah, thanks, Dr. Mark, for the excellent talk today. And I must thank once I came from Antarctica, and that time we had the Sentinel 1A and 1B. So 6 days coverage was there. So I was getting very good interference for the glacier velocity. In the 12 days, there is a loss of coherence. But then I requested ESA, they accepted my request. And 2-3 next year also, I got the 6 days. So that was my personal experience. And in future, if the 6 days coverage is there with the two satellites, it gives very good results for the high mountain Asia also.
I emphasize this, but of course we lost Sentinel-1B in the meantime. So we're in the process of trying to get Sentinel-1C launched. Now we have a launch date early next year. We're launching Sentinel-2C in the meantime, in a month or two, on the next Vega flight. And so the problem that we've had temporarily with our launches is being resolved, and we're hoping to get back to completing the Sentinel-1 constellation with a C and a D satellites in the next year or two. And then we will be back up to full operational monitoring capability with the 6-day revisit. As we add, of course, the next generation, we'll provide the continuity to this 6-day, and I hope that the launcher situation doesn't prevent us from maintaining the operational constellation in the way it was designed. It's unfortunate that we lost Sentinel-1B, but at least 1A is still functioning fine, and it just doesn't give the temporal resolution that we would like, of course, for cryosphere applications.
Thanks, sir. And I invite you for next Wednesday also. Our NISAR, we are keeping our fingers crossed. So early
Yes.
next year, we have the launch of NISAR, a dedicated interferometric mission for.
I learned of the launch date just yesterday after
Yes.
the rescheduling, and I hope the work that was done on the antenna has resolved the issue that I know from Paul Rosen about a little bit in detail, and so now the launch is scheduled. It's fingers crossed for a very successful launch, and this addition of L-band data in the future, which is back to CSAT.
Yes.
back to my roots.
Yes. So many thanks, sir. Hopefully you can spare some time for the next talk also to listen to Dr. Paul.
I'd love to do. Yeah. Thank you very much for the information, and it's been a very interesting opportunity. I hope I answered anybody's questions. I'm available by email, of course, and anybody who wants to ask me a further question, welcome to do so. You can find me at mark.drinkwater@esa.int.
Yes, yes. And we will need your permission that we can host the recordings of today's session with our society
Of
members.
course, you're welcome to do so, and it's to everybody's benefit that they have access to this information, especially the web links and the sources of information, which will be useful for follow-up.
Yeah. Thank you, Dr. Mark. Thank you, Nick, for nice coordination. Today my internet was stable, no more hiccups.
Perfect. Very good.
Yeah.
Very good.
Yeah.
Thank you, everyone.
Thank you.